So since they're finding my slides, I want to thank the organizers for letting me share my work with you all. And I also want to thank the audience for sticking around till the last talk of the day. So, so I'm going to talk today about using neutral hydrogen velocity dispersion to trace the dark matter in galaxies. Now, this is a little different from the usual approach because usually one uses the galaxy rotation curves to trace the dark matter. But I'm going to try to convince you in this talk that H1 velocity dispersion is equally good. Now, this is the quick outline of my talk. Initially, I'll talk about the observational and simulation studies of dark matter halo shapes. And then I'll just talk about how oblateness or prolateness affects galaxy disk dynamics. And then I'll go on to the three projects where I've tried to explore the dark matter halo shape and dark matter halo distribution using neutral hydrogen velocity dispersion. And there are several people involved in this work, which has taken a couple of years. But I'd like to mention Amruta, who's doing a PhD with me at IIA, and Roger, who is in Institute Astrofísica in Andalusia, Spain. Okay, so let's just quickly talk about the observations, evidence that we have for halo shapes. Halos, as we know, in the mid 90s, showed a lot of varieties of polar disks, and these polar disks were very useful because they extended way out into the galaxy halo, and with models you could try to estimate the halo shape and the halo prolateness or oblateness. Another method that was used is the hydrostatic equilibrium of galaxy disks. An example is given here, done by Olling in 96, where this is the edge-on galaxy, dwarf galaxy, NGC 4244. And if we assume that there is an equilibrium in the disk between the gas and the disk, then we can use the hydrostatic equilibrium to determine the dark matter associated with it. Now, this was used for the Milky Way, and Chanda and Arunima used it to find out the shape of the Milky Way halo, and which they suggested was prolate. And more recently, with Gaia observations, the distribution of globular clusters has been known to indicate the prolate shape of our Milky Way halo. Now, simulations have also been very good at understanding galaxy halo shapes. And this is a very early one by Dubinsky in 94, where he used simulations of a galaxy halo where there was gas infall. And as the gas infall proceeded, there was adiabatic contraction, and the plane of the galaxy, the disk of the galaxy, the halo in that plane became more circular, whereas the shape was either prolate or oblate. Now, recently, cosmology simulations have improved on this because they have included the nuclear activity of galaxies, star formation and AGN outflows, which can push the dark matter out along with the mass into the outer parts of the halo, thus creating a different halo shape around the galaxy. And one thing I want you to just notice here is that if you look at the C by A, which is the z-axis and the x-axis, you can see that it has mostly a variety of values, whereas the disk plane B by A is close to 1 for most of the cases, which indicates that in the disk plane of the galaxy, the disk is circular, but in the perpendicular plane, it can be oblate or it can be prolate. Now, we investigated how this affects the disk dynamics, and one of the aspects that we explored was bar formation, because bars is a very good way to understand disk stability and disk properties. And this was done by Ankit a few years ago. And so what he did was he looked at how bars are forming in different n-body simulations with halos which are live. And what we discovered is that bars form later when we have oblate halo. So when the halo dark matter is more associated with the disk, the bars form later. Now, one of the reasons for this is the velocity dispersion of disks increases as you have more and more mass associated with it. And when you have an oblate halo, you can see over here that the velocity dispersion is increasing, and the Tumbre instability factor is also increasing. And he also showed that bar buckling is more predominant in prolate halos, where there is the gravitational force by the disk dark matter and the dark matter halo allows the buckling of the disk and bar. So now I'll move on to the main topic of this talk about how we are going to use disk, how we are going to trace the disk dark matter with neutral hydrogen velocity dispersion. Now, as I mentioned earlier, hydrostatic equilibrium of disks has often been used in edge-on galaxies, where there is a balance between the pressure of the neutral hydrogen along with the stellar matter. However, when you look at galaxies like this, galaxies which have large neutral hydrogen disks, but very limited stellar disks, the question arises is where is the gravity that contains this really extended neutral hydrogen disk? And this is a question that drove this work, and especially important for the low luminosity galaxies and the ultra diffuse galaxies, which we heard about today. So these are our main questions. How is the vertical equilibrium maintained in extended H1 disks of galaxies where you hardly see any stellar matter? Where is the gravity? Is the gravity dominated by the halo dark matter in those cases? And can we use this disk dark matter to also trace the halo shape? And lastly, this is a recent work we started. How is the dark matter distributed within the halos? Can we apply this to Leo T, which is a nearby, very close ultra diffuse galaxy? Now, the main basic equation is an equation that we are all familiar with, the hydrostatic equilibrium equation, where in the z direction, we are assuming that the equilibrium is decoupled from the radial direction, the equilibrium in the radial direction. So you have the velocity dispersion here with the neutral hydrogen density, and on the right-hand side, you have the potential, and applying Poisson's equation, you can reduce this to give an expression for the dynamical disk matter. Now, the dynamical disk matter is given by the velocity dispersion, and this is in the z direction, and of course, the thickness of the neutral hydrogen disk. So these are basically the two parameters that are going into deriving the dynamical mass of the disk at each radii of the galaxy. Now, we can only apply this to regions where there is no star formation, because star formation produces a lot of turbulence in the interstellar medium, and you can't really include it in this equation because you are assuming an equilibrium. There can be some equilibrium, but that is a little hard to model. So we have really applied this equation to the extreme outer disks of galaxies at R25 or beyond. Now, if you take the dynamical mass at any radius of the H1 dominated galaxy and you subtract the baryonic mass, which is the neutral hydrogen mass, then it will tell you the dark matter associated with the disk. So initially, we have applied this to about 8 galaxies, of which several were massive galaxies and several were the dwarf galaxies. And what we found is that the dwarf galaxies are more dark matter dominated. So their disks are associated with larger dark matter masses. And this is to be expected because a lot of other simulations and semi-analytical studies have also showed that low luminosity dwarf galaxies are dark matter dominated. Now, we carried this a little further by assuming a form for the density of the dark matter, which is associated with the disk. Disk dark matter can actually also be accreted from mergers, but in this case, we assume that it was part of the dark matter halo. And so in this expression, there is a Q factor which can give you the axis ratio of the halo. So if this Q is greater than 1, it is a prolate halo. If it is less than 1, it is oblate. And if it's close to 1, it's just like a spherical halo. So this we applied, and we used a large sample of galaxies from little things and the VLA Angst survey. And so the sample was 12 dwarf and 8 high stellar mass galaxies. Now, I won't go into the details. I just want to show you 2 plots that were very interesting from this study. The first one shows that the oblateness parameter Q is kind of correlated with the stellar mass of the galaxy. And this is a loose correlation, and there's a little bit of a gap here. So we need more galaxies. But there is definitely a trend that the galaxies appear to become more prolate as they become more prolate, or even spherical as they become more massive. And the more interesting correlation was that if we divide the sample into two, the gas-dominated the galaxies and the stellar-dominated galaxies, what we find is that the gas-dominated galaxies are all oblate. They have an oblateness parameter which is less than 0.55. But the stellar-dominated galaxies have a distribution of oblateness. And one of the reasons, the kind of thought behind this for understanding, we found that the halo spin of the dwarfs can, and the tidal torque interaction in the early epochs might be a reason why they have more oblate, because as you spin, you will flatten out. And now I'll move on, because there's not a lot of time, to our study on Leo T. Leo T is a very ultra diffuse, very faint galaxy, and it's only about 400 kiloparsecs away, so it's very close. It's quite close to the galaxy Milky Way plane, and you can hardly see it. If you look at it in even decals, I was only able to really see it in the G-band image. Now, we have been looking at the stellar distribution in this galaxy. The reason why we chose Leo T is that in a recent Muse study of all these nearby satellite and really dark matter-dominated galaxies, Leo T was the only one that showed signatures of star formation. This work was done by Daniel Vaz, and what he found is a distribution of stars, which were mainly old stars, which are the red circles and the blue ones. And we have looked at it in UVIT, and we find FUV emission associated with this UDG galaxy. And I think this is the first time that FUV emission, or even any UV emission, and this UV emission comes mainly from evolved stars, blue stragglers, maybe also some white dwarfs. Now, the next thing I want to talk about is how is this stellar distribution located. Now, the contours here are the neutral hydrogen contours, and I'll talk about it in the next slide. Oh, can I have 2 more minutes? Okay, so let me just show you the H1 distribution and show you, yes, and I will end with this. So this is the moment 2 map, which shows the H1 velocity dispersion on a 2-dimensional plane. If you subtract the moment 0 map, which is the H1 distribution, you will get the dark matter distribution. The dark matter distribution you can see here is not only is it lopsided, it has a shallow potential well in the center. I'll stop here then.
Thank you. Questions?
Sorry, so when you are modeling for the velocity dispersion, are you assuming the thickness of the disk not vary with radius?
Yes, for this preliminary study, I've assumed it as constant thickness. I've taken different values. This one was 150 parsecs.
But if you assume it to
out, then we will probably do that. But what when I've looked at the literature, the dwarfs don't really have much warping. It's only the massive galaxies that really show a warping after R25.
Not warping.
Or
flaring.
Flaring, yes, even flaring they show after R25 or 1.5 R25.
That must be a very nice talk.
Thank
you. You made a statement that star formation introduces turbulence in the medium. So why does it happen, and how would you observationally quantify this?
So it happens because of the stellar outflows. So when in a cluster, when there's star formation, the massive stars will give out stellar winds, and these stellar winds will deposit kinetic energy into the rest of the interstellar medium, creating turbulence. So if we were to model it in this, then I would add another term I've just put as velocity dispersion here, but coming from the moment map. But I guess another term might have to be added. Or we would have to take that and divide it into a turbulent component and a not so turbulent component.
Okay.
Difficult.
Okay, thanks.
Okay, any other question?
Everyone is tired.
Well, if not, let's thank Mousumi for this talk. And then we also thank all the speakers, all 4 speakers of this session.